Okay, let's do another example of a related rate problem. This is number 13 on page 194 in the textbook or the PDF doc. The radius of a sphere is increasing at a rate of 3 inches per minute. Find the rate of change of the volume when r radius is equal to 9 inches and when r is equal to 36 inches. So the first thing again that we want to note here is we want to put in and note our volume equation. So let's go ahead and insert an equation. And the volume of a sphere is equal to 4/3 pi times radius cubed. When you're dealing with a volume, you have to have a combined cubic dimension. And in this case, our only dimension for a sphere is its radius. And so that radius has to be cubed in order to have a volume. Other important things to take note of in this problem, we should probably look at our other values here. We've got r equals 9 inches and r equals 36 inches. So we'll write those down. R, it wants to capitalize it. So let's put it in as an equation, then it won't. R equals 9 inches and r equals 36 inches. We're only going to focus on doing the first one, the r equals 9 inches, because once you've done that, then you're just plugging in a different value. And it's important for us to make the note again that these are changing dimensions. If it was a constant dimension, we could plug it in right away. If we had a constant 9 and we plugged it in right now, we'd get volume equals a number. And if we took the derivative of that, we would get rate of change of volume is 0, and that would not be true. So it is important to recognize which dimensions are changing versus which dimensions are constant. All right, let's take our derivative. Let's bump our equation size up a little bit here again, because we'll have fractions in this. And let's start with our derivative. I didn't make it a fraction. We want to find the time derivative of our volume equation. I probably should have just copied and pasted it from up above. 4/3 pi r cubed. And that is going to be equal to fraction derivative of volume dv dt is equal to, using our power rule, 3 times 4/3 is going to give us 4 pi r, subtract 1 from the exponent, is now squared. And because our radius is not a time, we have to add our rate of change notation here, dr dt. And now we've got our equation, and as we take a look through it, we're trying to find the rate of change of volume. That's going to be our outcome. We have been given a dr dt to plug in. We didn't note that. We should have noted that. Radius of a sphere is increasing at a rate of 3 inches per minute. So let's go back up here and add that in here, that we know that dr dt is equal to 3 inches per minute. So we have a dr dt to plug in. We have a radius of 9 to plug in. We're going to simplify that. We're going to get a solution. And this is a pretty simple related rate problem for us to complete. So new equation, fraction dv dt is going to be equal to 4 pi times 9 squared. And I'm going to write that as 9 inches squared, because we want to make sure we get our units correct here. and that is multiplied by 3 inches per minute. If we go through and simplify that, 9 squared would give us 81. 81 times 3 would be 8 times 3, 243. 243 times 4 give us an answer of 972 inches cubed per minute. And if we double check the answers in the textbook, number 13, we get 972. All right, we forgot something. What did we forget? 972, there should be a pi in here. Not forget that. 972 pi inches per minute. I don't know why I just did that. I'm trying to bring it all onto one spot so we could see it all. Final answer. 36 inches is going to come out to a much larger number because we're going to square 36. But it's really not any different. You're just going to be plugging in different values. Be careful with your units. Make sure your units are correct. Remember, we're dealing with a rate of change of volume, so we have to have a volume unit, something cubed, per some unit of time, in this case, minutes. Let's talk about part B really quick. Down here. Part B said, explain why the rate of change of volume of a sphere is not constant, even though dr dt, the rate of change of the radius, is constant. A very simple answer to that is when we look at our equation for rate of change of volume, dv dt is equal to 4 pi r squared, there's a variable in here. If dv dt was going to be a constant, you would have had nothing but constants in this derivative. And we have a constant dr dt, and we have a constant 4, and we have a constant pi, but we have an r value here, a variable radius. The radius is continuing to change, so the dv dt will continue to change. Anytime you've got a variable in your derivative, you're going to have a rate of change here that's not a constant. And that's the very simple answer to that one. So I hope this one was helpful, and we'll move on to another example shortly.